Hello, I'm going to introduce you the fitted value approach here. So in the last lecture, in the last week, I have explained how we can identify in the general case using the IV moment approach. Excuse me. Anyhow, it took some quite a bit of time, but it is important. It was important. I explained the intuition behind the rank and how you find the solution. So basically, identifying on a parameter is basically mathematically finding a unique solution, whether the solution is unique or not. And today we are going to use the fitted value approach. And already at the beginning of this chapter, earlier in this lecture note, I have introduced you the same approach with scalar variable. So if y is scalar, x is scalar, then the fitted value approach was simple. But now we are handling a more general vector notation case. So you have to be careful about the dimensions. I explained it at the end of the last video, so I will skip that briefly. So then remember, the main idea here is x2 is endogenous. So our original regression equation is only this. The second stage, the structural equation was the only regression equation we had originally, but we intentionally add another regression equation for the endogenous variable. So remember, the meaning of the endogenous variable is that, so endogenous means the variable is generated within the system, like endorphin. So if morphine is generated from our body, then that's endorphin, like endogenous morphine, something like that. So anyhow, a variable, this is endogenous variable. So we explain how this is generated within our setup, our model. That's what we would like to do in this approach. So we set up the equation for x2, and then what we are going to do here is, remember, the main reason we had problem in x2 is because x2 is correlated with epsilon, and our goal is to decompose the endogenous variable x2 into the part that is uncorrelated with epsilon plus another part that could be correlated with epsilon. So in this case, these guys are uncorrelated with epsilon, but psi, the residual, can be correlated with epsilon. So the problem is coming from psi, not from these guys. So we are going to use the variation only in the first part, and the first part that is uncorrelated with epsilon. So that's the main idea we are going to do. And then how can you do that? First, observe that identifying gamma 1, gamma 2, by the way, they are matrices. Gamma 1 is a matrix, gamma 2 is another matrix. So identifying gamma 1 and gamma 2 is straightforward. It's linear projection. It's not even, it's a reduced form regression. So you can call this linear projection. So whenever you have variables x2, x1, z2, you can calculate gamma 1 and gamma 2. And then psi is the residual from the linear projection. Or you may use the classical linear regression assumptions. This equation, by definition, satisfies the classical linear regression assumptions, so gamma is identified. There is no problem in calculating or identifying gamma from your data. And then, so this step is not that bad, but what you need to do here is you are going to replace x2 in the second stage equation with this full equation. So replace that, and then we are going to put psi together with epsilon, the error term. So in the second stage, the actual error term you are going to handle is a bigger one, psi beta 2 plus epsilon. So this is your error term, but another difference here is originally here was we had x2, and the place of x2 in that place of x2 we have x2 hat, which is defined as, where did we define that? I did not define it at all. Oops. So x hat is this guy or this guy. So we are going to use the fitted value from the reduced form equation from the first stage regression in the place of x2. So x2 hat will be used, and then you identified x2 hat. So it's not a problem using x2 hat, and then beta 2 can be identified if this equation satisfies the classical linear regression assumption. So the classical linear regression assumption is satisfied because of this. So it's easy. I believe you can check if the equation satisfies the classical linear regression assumptions or not. And then this is just a simple, straightforward extension of the one-dimensional fitted value approach. So we already learned one-dimensional case, and this is general dimension case with vector and matrices. Just be careful about matching the notation and the dimensions. Here it is. So x hat is defined in this way. And then so beta, from the second stage equation, we have beta defined in this way. Remember, this is the how we identified the classical linear regression. So using the same formula, we have this guy, and using the same derivations. And gamma is from another regression. So we are using regression twice in the first stage and the second stage. So gamma can be written in this way. So plug this gamma, this expression, into here and use that expression into x hat. Then it will be very cumbersome, very tedious algebra. But in the end, you are going to have something still very complicated. In the end, still complicated, but there is a pattern. So there is a pattern here. This part and this part are the same. So something inverse times something. But so this guy and this guy are the same. And what it means is this is what we learned here. So when I introduced you the first approach, I told you that the weight matrix, the matrix, you have to multiply a matrix to match the dimensions. And I could not explain why, but I told you that the commonly used matrix for A is this. And then the assumptions are consistent with what we use for the fitted value approach. And in fitted value approach, as a result, you get that matrix, and then is exactly the solution is exactly what you got here. So if you look at the algebra carefully, you should be able to see what they share from two different approaches. Okay, let me resume the next chapter in the next video. So I will stop it here. See you. Bye.